Understanding the binary number system can be important when working with protective relays, especially modern digital or numeric ones. Here are a few reasons why. 1. Configuration and settings. Many digital protective relays use binary codes for configuration and settings. Knowing how to interpret and manipulate these codes can help you set up the relay accurately. Number 2. Communication protocols. Protective relays often communicate with other devices using protocols that rely on binary data. Understanding binary can help in troubleshooting communication issues and ensuring proper data exchange. 3. Logic functions. Digital relays use binary logic for decision-making processes. Understanding binary logic can help design and understand the relay's operation and action schemes. And 4. Programming and customization. Some advanced relays allow for custom programming using binary or hexadecimal codes. This can be crucial for creating specific protection schemes tailored to unique system requirements. While not the only skill necessary, understanding the binary numbering system can significantly improve your effectiveness with protective relays. The binary numbering system is a numbering system that represents numeric values using unique digits, 0 and 1. Computing devices use binary numbering to represent electronic circuit voltage state, example, on and off switch, which considers 0 voltage input as off and 1 input as on. The binary system is also known as the base 2 numbering system or the binary numbering system. This numbering system is basically the same as the decimal or base 10 number system, except only 2 digits are used, 0 and 1. Binary numbers are made up of binary digits, which are called bits. Note, bit is short for binary digit. Bits are not meaningful on their own. Typically, they will be grouped together. One key grouping is 8 bits together, which is called a byte. A byte can represent 256 values, ranging from 0 to 255. And all zeros binary byte equals 0 in decimal. And all ones binary byte represents 255 in decimal. To understand binary numbers, begin by recalling elementary school math. When we first learned about numbers, we were taught that in the decimal system, things are organized into columns, such that H is the hundreds column, T is the tens column, and O is the ones column. So the number 183 is 1 hundredths plus 8 tens plus 3 ones. Years later, we learned that the ones column meant 10 to the power of 0, the tens column meant 10 to the power of 1, the hundreds column 10 to the power of 2, and so on, such that the number 183 is really 1 times 10 to the power of 2 plus 8 times 10 to the power of 1 plus 3 times 10 to the power of 0. To count in the decimal system, we start at 0 and we count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we start back at 0, but we add 1 on the left. 10, 11, 12, all the way up through 99. Then we start at 0, but add a 1 on the left. 100, 101, 102, and so on. The binary system works under the exact same principles as the decimal system, only it operates in base 2 rather than base 10. In other words, instead of columns being 10 to the power of 2, 10 to the power of 1, 10 to the power of 0, they are 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. To count in the binary system, once again we start at 0. Count 1, and then we start back at 0, but we add 1 on the left. 1 0, 1 1. We start back at 0, but add 1 on the left. 1 0 0, 1 1 0, 1 1 1. Start back at 0, but add 1 on the left. 1 0 0 0, 1 0 0 1, 1 0 1 0, and so on. Binary numbers are written from right to left. The first bit is represented as 2 to the power of 0. The next as 2 to the power of 1. The next as 2 to the power of 2. The next as 2 to the power of 3. The next as 2 to the power of n plus 1, and so on. Next, let's look at converting binary to decimal. What would the binary number 1011 be in decimal notation? Well, the first thing we notice is that we have a 4-bit binary word. Therefore, let's start by setting up our columns. Now let's enter the decimal values for each column. The first bit position is equal to 1 in decimal. The second bit position is equal to 2 in decimal. The third bit position is equal to 4 in decimal. And the fourth bit position is equal to 8 in decimal. Let's look at our binary word 1011. Each bit in the word with a 1 is now added to any other bit with a 1. The first bit is 1 times 2 to the power of 0, which equals 1. The second bit is 1 times 2 to the power of 1, which equals 2. The third bit is 0 times 2 to the power of 2, which will equal 0. The fourth bit is 1 times 2 to the power of 3, which equals 8. Now we add each bit position that has a 1 in it. So the binary word 1011 is equal to 11 in decimal. Okay, now you try it. Convert the following binary numbers to decimal notation. Start with 1100, then go on to 1111, and finally convert 1001. Congratulations if you got the following answers: 12, 15, and 9. Remember, when converting binary to decimal, take the binary number and place it into the appropriate columns for two-base numbering system. Give each column its equivalent decimal value. For example, 2 to the power of 4 equals 16. 2 to the power of 3 equals 8, and so on. Each bit in the word with a 1 is then added to any other bit with a 1. Okay, what about converting decimal to binary? Converting from decimal to binary notation is slightly more difficult conceptually, but can easily be done once you know how using algorithms. Begin by thinking of a few examples. We can easily see that the number 3 equals 2 plus 1, and that this is equivalent to 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. This translates into putting a 1 in the 2 to the power of 1 column and a 1 in the 2 to the power of 0 column to get 1, 1. Almost as intuitive is the number 5. It is obvious 4 plus 1 equals 5, which is the same as saying 1 times 2 to the power of 2 plus 1 times 2 to the power of 0 equals 5. Looking at this in columns, 2 to the power of 2, 2 to the power of 1, 2 to the power of 0 would be represented as 1, 0, 1. What we're doing here is finding the largest power of 2 within the number. 2 to the power of 2 equals 4, which is the largest power of 2 in the number 5. Subtracting that from the number 5 minus 4 equals 1, and finding the largest power of 2 in the remainder. 2 to the power of 0 equals 1, which is the largest power of 2 in the number 1. Then we just put this into columns. This process continues until we have a remainder of 0. All right, let's take a look at how it works. Let's convert 107 to binary. To start, we need to find the highest power of 2 for 107. The highest power of 2 for 107 would be 64. Therefore, we place a 1 in the 64 column and subtract 64 from 107, leaving us with 43. Now we find the highest power of 2 for 43. The highest power of 2 for 43 would be 32. So we put a 1 in the 32 column and subtract 32 from 43, leaving us with 11. Now we find the highest power of 2 for 11. The highest power of 2 for 11 is 8. Therefore, we place a 1 in the 8 column and subtract 8 from 11, leaving us with 3. Now we find the highest power of 2 for 3. The highest power of 2 for 3 is 2. Therefore, we place a 1 in the 2 column and subtract 2 from 3, leaving us with 1. Now we find the highest power of 2 for 1. The highest power of 2 for 1 is 1. Therefore, we place a 1 in the 1 column and subtract 1 from 1, leaving us with 0. Since we cannot go any further, the binary number for 107 is 0, 1, 1, 0, 1, 0, 1, 1. All right, now you try it. Convert the following decimal numbers to binary words: 249, 164, and 27. And congratulations if you got the following answers: 11111001, 101000100, and 0001111. Remember, when converting decimal to binary, find the highest power of 2 for the decimal number you're converting and place a 1 in that column. Then subtract that power of 2 from your number. Then find the highest power of 2 for the remainder. Continue this process until you reach 0. In summary, the binary number system is a numbering system that represents numeric values using 2 unique digits, a 0 and a 1. It is a base 2 numbering system. Binary bytes are represented by the following columns: 2 to the power of 7, 2 to the power of 6, 2 to the power of 5, 2 to the power of 4, 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, and finally 2 to the power of 0.